Hello, hello. This is section 6.4 from James Stewart's Calculus Early Transcendentals book. And today we are talking about applications of integration, and the topic is work. So we're going to go over some units of measurement in the standard international units of measure and also the U.S. customary. And we're going to go over a couple of applications of work. So first, a force is a way to describe the push or pull of an object. And we know that from Newton's second law, the force exerted on a body with mass m, moving along a straight line with the position function s of t, is given by the formula force equals mass times acceleration. And if that is the position function, remember your derivative s prime would be your velocity, and your double prime would be your acceleration. And this is what the second derivative d2 s of dt squared, that is a second derivative a of t. Good. Most people who study physics or engineering recognize that formula as force equals mass times acceleration. And normally your mass is counted or measured in kilograms, and acceleration, if we've got position in meters in the international units and time is seconds, then velocity would be meters per second, and acceleration would be meters per second, and that would give us meters per second squared. And we want to call the kilogram meters per second squared, which is the force constant or the force measure. We can say that that unit of measurement is called the Newton after the Sir. We also want to note that mass describes the amount of matter in a body, while weight, talking about the U.S. customary units of measurement, while weight is the force acting on a body due to gravity. So your mass is going to be constant everywhere in the universe. However, your weight will differ from planet to planet because the acceleration due to gravity is different on each planet in the universe. All right. So the definition of work or mechanical work is the amount of energy that's transferred by a force acting on a body through a distance, d. And the formula for work is this one. Work is defined to be force times distance. Okay, and when when force is a constant and distance is a constant, then it is very simple to just go ahead and use the formula force times distance. And if we are in the standard international metric system, force would be kilogram or newtons, right? And our distance would be in meters. And so we would have Newton meters, and they rewrite that or recall that equivalent to the joule. Okay, so newtons is kilograms meters per second squared. That comes from mass times acceleration. And the joule, which is the unit of measurement for work, is the Newton meter because it's force times distance. So we're going to go ahead and do a couple of examples in where force is constant and distance is constant. That's when we don't need to use any calculus. We can just go ahead and multiply the force times distance. All right, so here it says how much work is done to lift a 1.2 kilogram book from the floor to a shelf 1 meter high. Use the fact that the acceleration due to gravity is 9.8 meters per second squared. So whenever you're given kilograms and you're working with work problems, make sure that you multiply your kilograms by g, which is 9.8 meters per second squared. This is our acceleration due to gravity. Good. So we can start off with our kilograms, or our mass is 1.2 kilograms. That means our force is going to be mass times acceleration, so that's going to be 1.2 times 9.8. And if we multiply that together, we'll get 11.76, and that is going to be in newtons. And now we have what distance do we want to move? Just 1 meter. And so we have constant force, constant distance, so we can just go ahead and multiply those together, and we get work is force times distance. And that's going to be 11.76 newtons times 1 meter, and we'll end up with 11.6 newton meters. Or we can say that that is 11.76 joules. Good. And in the second example, we see that we're in U.S. customary units of measurement. A mother pushes a stroller 25 feet along a flat sidewalk with a force of 20 pounds. Determine the amount of work. So we have that our force is equal to 20 pounds. Our distance is 25 feet. And so our work, since both force and distance are constant numbers, our work is just force times distance. And so we're going to have that this is going to equal 20 times 25, and that's going to give us 500 foot-pounds. And we don't have a special name for the U.S. customary work units. We just use foot-pounds. So I created a small little list of summaries of units of measurement for your standard international units of measurement, otherwise known as the metric system. Your distance is usually measured in meters or centimeters. Your mass is measured in kilograms. Your force is mass times acceleration, and so its units are kilograms meters per second squared, and that has a new unit of measurement called the newton. Work is force times distance, so it would be newtons times meters, and that has a new unit of measurement called the joule. The acceleration due to gravity constant on Earth is 9.8 meters per second squared, and don't forget to multiply your kilograms by that if you need a force value in your applications. The U.S. customary units of measurement, we've got distance is either measured in feet or inches. Our weight is in pounds. Our force is also in pounds, so just consider weight to be a unit of force. And our work units of measurement are foot-pounds or inch-pounds. So you can use either one, but neither one of them has a special name like joules. All right, so make sure that you keep track of your units of measurement. I find that looking at units of measurement in various applications really helps me to solve problems. So I will continue to emphasize that. Okay, so what happens if we've got a variable force? In other words, force is not constant the entire time that we are pushing an object or pulling an object. So suppose that we are dealing with a variable force with respect to the body's position. How do we measure that work done in moving the body from one point to the other? Well, we can introduce our Riemann sum. We can introduce calculus. Like what we did with areas under curves, we would break it up, because noting when we found areas under curves, we would break up our interval into subintervals and estimate along that any arbitrary interval. We'd estimate it with a rectangle, and that rectangle would have a variable height from rectangle to rectangle in the partition, but we'd let the number of rectangles go to infinity when taking the integral, right, behind the scenes. So that's exactly what we do here. If we've got a variable force just along this delta x slice, we can assume that the force would be constant at one particular value along that. That's what we do with an approximation, knowing that when we put it behind an integral, we're letting that delta x go to 0. So we really can, along that slice of our variable force, consider the force to be constant there. And we would be kind of, in a way, and when we form our Riemann sum, we would be saying how much work is it to push the object from A to the first, and then we would change our force amount, and then we'd go another delta x, we would change our force amount, go another delta x, change our force amount, and calculate our work with each slice, and then we would add up little increments of work, and adding up the increments of work and letting the number of our partition go to infinity, we end up with work is just that force times the dx. So our delta work here as our slice would be our f of x, which is our force function, times distance. And our distance would only be going delta x before we would go and recalculate another one. And then we note that our total work is going to be the integral of our delta work. And our limits of integration will be the distance that it needs to be moved. All right, so taking a look at this example, when a particle is located a distance of x feet from the origin, a force of x squared plus 2x pounds acts on it. So I look at pounds and I know, okay, I don't need to multiply by 9.8. My unit of measurement for force is pounds in the US. How much work is done in moving it from x equal to 1 to x equal to 3, and we know that this is going to be in feet, right? So we would say delta work here is f of x times delta x, and our f of x is x squared plus 2x delta x. And our total work is going to be the integral from 1 to 3 of delta work, which is 1 to 3 of x squared plus 2x dx. And so we would end up with x cubed over 3 plus 2 times x squared over 2, which is just x squared. And we'd be going from 1 to 3. And that calculates to 27 divided by 3 is 9, plus 9, take away 1/3, plus 1. And so we would end up with 18 minus 1 1/3, which would be 16 2/3, right? And our unit of measurement would be foot-pounds. Okay, good. So that's what happens when we have variable force. We use calculus, not just force times distance. All right, I'm going to stop here because I'm going to use different videos to present when we have variable distance and how to apply those. So we're going to have an instance where when we lift ropes, if we're just lifting the rope is going to usually have a particular density, and you'll see, like in this case, this rope has 2 pounds per foot, and so if we just multiply by feet, we'll get to pounds, and we can get to our unit of measurement of force. But in instances of lifting ropes, we'll be using variable distances that we can isolate each partition where we would have constant force, but the distance will vary. Same thing when we go and use another application, pumping fluids out over tanks or emptying pools of liquid. We'll be using variable distance there too, but when we create our slice will have uniform force for each slice. And sometimes, depending upon the shape of the tank, we could have variable force as well. So we'll be looking at applications of that. And also with pulling springs, well, that will be another application of variable force. Good, so be on the lookout for part 2, part 3, and part 4 of this section on work.